Hello, everyone, and welcome to GP Tuesday, a weekly AI event where we bring together AI engineers, enthusiasts, programmers, researchers, and everyone that's interested in AI into one place so we can all learn together and stay ahead of the AI wave of change. Thank you again, everyone, for making it. Today, we're going to have a very special presentation. We're going to be talking about, Aleksey will be presenting on frontier AI from DeepMind's nuclear fusion all the way to PyTorch Lightning. But before we get into that, let's talk a little bit about our sponsors here. We have the Hub, gracious enough to let us be here every single week so that we can bring AI education to everyone here. They have amazing desks. The prices are very reasonable. I actually work out of here, so if you want to hang out with me as well, I'm always here. So go ahead and get a desk. They have great offices and offices that look outside too. So come swing by anytime and ask front desk for any desks and anything else. Other items are that we have parking validation. Go ahead and just go to the front, and we'll get parking validation for you. But before I take too much of the time up here, let's give a round of applause for Aleksey.
All right. Hi, everyone. Thanks for coming. My name is Aleksei. I moved to Miami from Russia 3 years ago. I'm very happy to be here to present today. This is actually my first public speaking in English. I hope I'll be doing great. So, the motivation for this presentation is the following. We mostly hear a lot of news about models like Stable Diffusion, ChatGPT, and if you think about it, most of them about entertainment. We generate some pictures, videos, we generate some content. Some of it can be used for education purposes. We can even write code, other stuff. But in general, it's mostly driven by entertainment industry. What I'm going to talk about today is another side of AI applications, which is currently driving natural science and fundamental research. And before I start, I'm going to share a little bit about my background. I have 8 years of experience in machine learning and data science. Before I started my work at Grid Dynamics, I was a software engineer. And I also have a master's degree in computer science, and I was associate professor in computer science department in machine learning specialty. And I have experience in building different machine learning models. And first of all, I want to talk about Tier 1 AI teams. This is I think the main teams that are driving AI industry. And I think many engineers are dreaming to join these teams, and these are some of them. First is DeepMind. DeepMind was founded in UK. It was a standalone company before, and now it was acquired by Google, and it's part of Google Brain team. Next one is Meta. It's a research team inside Facebook. They created PyTorch. They created a lot of research papers in AI and useful frameworks, useful models. If you go and check their public repository, you'll find a lot of useful stuff there, like Llama. Another one is Microsoft Research, Google Brain, OpenAI, Anthropic. It's rival of OpenAI, NVIDIA AI Research, Stanford AI Lab, and so on. The good thing about this AI team is that the content for this presentation I stole from their blog. each of these teams has their blog in the website, and you can go and check what the project they are working on. And you can find the research papers, you can find the results, and a lot of interesting stuff there. First project that catch my mind was nuclear fusion project that was recently DeepMind recently published in the blog how they improved efficiency for nuclear fusion reactors. I think we need to get a little bit background to understand the problem. What is nuclear fusion? First of all, you need to understand that nuclear reactors are powering our cities for many decades already, and but they're working on the process called nuclear fission, and a nuclear fission process is very powerful, and nuclear fusion is opposite process. So first of all, we need to understand how atom nucleus looks like, what it is. So each atom has three components. It's a positive proton, neutral neutron, and its negative electron. So these three components is very fundamental particles of the universe. And this process, nuclear fusion, basically driven by these fundamental particles. Basically, for nuclear fission, to get energy, we have to make the conditions where nucleus has imbalance between number of protons and neutrons, which cause instability in the nucleus, and then this nucleus starts collapsing, and this collapsing produces a lot of energy along this radiation. However, nuclear fusion process is opposite. Instead of collapsing nucleus, we have to bond together or join different nuclei, and when we join them together, we also this nucleus also produces a lot of energy, and there's no radiation. There is clean energy being produced from nuclear fusion. And this clean energy can be used in many industries. For example, it can be adopted even for space travels, or it can be adopted for personal reactors. We can use them in the machines, vehicles, and many things, but it's a very early stage now. This concept was introduced like 40 years ago. It was well known, but the progress in this field is very slow, because for now we have to put a lot more energy into this nuclear fusion process, and we get less energy, so it's not really effective for now. But I think last year we got already breakthrough, so it was the first experiment where we got more energy from nuclear fusion than we spent. So now we understand nuclear fusion process, and what's the problem with this process? It's actually very difficult to bond together two nuclei, because each atom has electrons, and these electrons prevents from nuclei to bond together. And first we have to separate electrons from the atoms, and when we separate them, we create ions. Ions doesn't have electrons, and we can put much less energy to join nuclei. So first step is to separate electrons from the atoms. And how we do this? To do this, we have to create extreme conditions basically, if we get the atom into the extremely high temperature, like millions of degrees at Celsius or even billions of degrees, and then we will get electrons separated from the atoms, and electrons will become free, and ions can be used for nuclear fusion. And this process also replicated in stars. Inside of stars, the energy that powering them is basically caused by nuclear fusion. So, and the plasma, it's a state of the matter. It's like a fourth state of the matter. So first we have solid, we have liquid, we have gas, and we have plasma state. And the problem with plasma, it's very hard to control. And the only reactors for plasma is called tokamaks. It's basically group of electromagnetic coils, and we can control these coils, and these coils will create magnetic field, and this magnetic field become trap for plasma. And if we get the plasma into the trap, we can control it, so it will not collapse, and we can sustain the process for nuclear fusion. And before there was programmatic way to control these coils, and it was very sophisticated programs, manually written by programmers, and it was very inefficient. So what DeepMind team did in partnership with another team of researchers, they created a machine learning model that operates these magnetic coils, all of them at once. So it basically controls electricity that manages coils, and it learns how to manipulate it. So, and you can see with in these blue dots, you can see the target or the trap, and how machine learning algorithm learn how to control plasma. And they were able to create very unique shapes. For example, here, this one was never achieved before, or this one, it was also never achieved before. So they were able to manipulate plasma very, very effectively. Another project, it's also a DeepMind project. It's in the biology. In the biology, we have very fundamental structures that called amino acid sequences. This amino acid sequences is like a programs for our proteins. And the proteins is very fundamental cells of our molecules of our bodies, of lives. And in the nature, we have 300 million known molecules of proteins. And in the human body, we have around 300,000 of them. And the problem with, which is called protein folding, it's basically the prediction of the shape and structure for the protein based on its amino acid sequence. You can understand amino acid sequence is like a program. And if we learn how to predict protein shape and structure based on amino acids, we will be able to improve the efficiency of drug discovery drastically. For example, recently we had a COVID-19 spread around the world. And to create a vaccine, protein folding was used. The researchers basically, they simulated, first they learned how to predict shape of the proteins for the viruses. and they created conditions, and they learned how the virus will behave in different circumstances, and they were able to create vaccine. So it's very, very fundamental process in drug discovery. And the project AlphaFold 3, it's the third generation of the AlphaFold model. In the first generation, DeepMind basically achieved a state-of-the-art level of the protein folding. There is a benchmark of the existing models for protein folding, and AlphaFold first got first position in this benchmark. AlphaFold 2, it was second generation. They were able to drastically increase accuracy of the existing models. They pushed the boundaries for these protein folding models, and their research paper became number 20th research paper in the rank of all research papers in the world based on the number of citations. And they created database of all protein molecules in the nature, and predicted based on amino acid sequences. And AlphaFold 3 is a third generation where they learned how to predict not only proteins, but also other life molecules like DNA, RNA, and others. So it's very, very fundamental methodology which can increase the efficiency for drug discovery. This is another project in the same field, but in my opinion, it's even more advanced. It's called ESM3. The team basically used large language models to simulate reasoning that generates sequences, amino acid sequences, along with protein shapes and its functions. So they created a general foundation model for very basic fundamental evolution process. They learned how to prompt initial tokens of the amino acid sequence, and they can control and manipulate the generation process. So they can generate any types and any shapes of protein molecules, and they can predict the functions, how they will behave in different circumstances. So I think it's a very, very promising approach, and using this approach, I think we can beat a lot of diseases. So you can see here in the first step, it's like a prompt, and they use generative model to generate more and more and more sequences in the protein molecule, and also they basically created embedding space for all molecules, and you can see the distribution. The dark part is some new molecules that weren't existed before in the nature. So if you go to organic field to non-organic field, there's a project in chemistry that also DeepMind recently worked on. It's called GNOME. In chemistry, there's a problem called material discovery, and material discovery it's a very useful application because we need very, very advanced materials for many industries, for medicine, for space, for telescopes, for batteries, and many, many others. The fields requires the next generation of materials, and the materials that existing in the nature, it's not enough for our human needs, and we need to create synthetic materials that that will basically fit our needs. And DeepMind created a machine learning system which has two pipelines. So first of all, the task was to create stable materials. It's basically crystals. And these stable materials can be used, like I said, in next generation of batteries and so on. And there's a problem with new materials that there are infinite number of combination of chemical formulas and its structures. It's like a very, very large amount of possible combination of these components. And DeepMind proposed to have two pipelines. In the bottom, they introduced a compositional pipeline. Compositional pipeline is responsible for generating candidates, basically compounds for chemical formulas, which ingredients we need to include in the material. And they use graph neural networks to encode these formulas. Second pipeline is called a structural pipeline. It used to generate candidates in terms of structure. There are thousands of studied structures in the nature for crystals, and this pipeline basically used the existing set of structures. And by combining this chemical formula and structure, we can predict the stability of the new material. And some of the materials were stable in terms of resistance to the temperature, to the pressure, and so on. Some of the materials were not stable. And after new materials was proposed by neural network, density function theory was used to improve the accuracy of the stability prediction. It's very computationally expensive tool, but it's used to train, to get feedback for their neural network. They used feedback loop from this component to improve the performance of their neural networks. So basically in the cycle, by predicting more and more stable materials, the neural network learned how to generate optimal chemical compounds and which structures to associate with chemical compounds. And they created a database of 2.2 million new materials, new crystals. And all of them are stable. And before we had 20,000 of existing stable materials in the database, and they introduced 2 more million. And in these 2 million materials, they have selected 380,000 of the extremely stable materials. There are beyond the existing boundaries of stability. And these 300,000 new synthetic materials can be used in many fields. Like I said, it can drastically improve our life. We can make much better batteries. We can make much more lightweight components for construction and so on. We can create resistant materials from the fire. Before I move on, maybe you have some questions I can answer. Maybe it's okay.
Are these materials going to be patented?
Sorry, I can't hear you.
Are they patented? Are they patented?
No, it's open source. You can get access to all of these materials. It's open source. It's available for research community.
So you can work with the materials without patent, right? So you can work with the materials, you can build it yourself?
Yes. So it's available for research community, you can get the formula and you can create your own materials based on that.
Question. Were you able to incorporate any data about which crystals would actually be easy to grow, maybe based on available materials or just, you know, like different growth scenarios? Or is it just, are you at the baseline of like, here's the model, industry can see if it works?
They didn't provide the details how these materials will function. They just created metrics that this is the level of stability. So they generated top list of the stable crystals in terms of their industry standards, but they didn't provide any additional details like how to use these materials. But some of them, they got an examples of new crystals. I think in this picture you can see the synthetic materials that they proposed, and they declare that this particular materials will be very efficient for some specific purposes. So in the paper you can read about them.
Question.
One more question.
To generating labels for stability, do they run these formulations for these like compounds through traditional chemical modeling software to determine stability?
Yes. Yeah, there is a computationally expensive tool that predicts stability, and they use it as a starting point to start training process. And they use active learning to improve their model performance.
How do you think it's possible to like democratize this capacity of state-of-the-art research to people who don't know about AI as much? Because this AI is very advanced. Most of the papers you just mentioned just recently came out, and it's like most of those people that written those papers have been in like, you know, they probably have PhDs and like probably been, you know, doing math for a long time. How do you think we can like rapidly accelerate the rate at which people learn about this?
I think these results are already well known in the industry for the research labs who work in the material discovery problem. They all know about this, so it's a very famous project. Even AlphaFold, they got 20,000 citations in their research paper. It's a very huge number. It's like top 20 ever. And in the particular field, all industry experts, I think they're using it. But if you don't work in the industry, I think you have, at least you have advantage in the business. If you need to create some very advanced system for your project, I think you can get access to the database, simulate based on your needs, and I think you can reuse the components that they proposed. But I had a conversation with one of the founders of the company who is building batteries in Miami, and he said that he wasn't actually satisfied with the results that they got. I think, like he said, that we need much more understanding of the materials. So they proposed materials, but there is no information about them. Like there is additional research required on them, like a lot of tests based on their properties before we can adopt them. And there's too many of them, like 380,000 is a huge number. And I think next tool could be useful if we could structure it somehow based on the properties. For example, these are temperature-resistant materials. These are pressure-resistant materials, and so on. But how to promote it? I don't know. I'm not an expert in the marketing. Okay, we can move on. In the fundamental math, there are also a lot of problems that are not solved yet. And DeepMind decided to build a system that can work in math problems, and they used a generative model for that. But the problem with generative models is that it can hallucinate when it generates new tokens. It can generate tokens that are not mathematically correct. And they proposed two levels of system, where first they get informal problem description, and they use a Gemini model to translate it to formal problem definition. There is a language called Lian to create formal statements for mathematical problem that can be used by solvers. And in the next step, they used their algorithm, very famous, called AlphaZero, to create proofs based on this formal problem definition. And these proofs also use active learning approach to solve mathematical problems and check their correctness. And iteratively, they keep improving the quality of solver network. So it learned how to solve more and more difficult problems. And at some point, it achieved almost gold medal in the International Mathematical Olympiad in 2024. So you can see that their model got 28 points in the benchmark and in the leaderboard. And they were so close to gold medal. And I think next year, they will be in the top leaders. And this system can be later adopted to solve existing problems in math that are not solved yet. And this could also open new doors in many industries like physics, engineering problems, and so on. Neuralink, you all probably know about this. It's first human-made brain-to-computer interface. And it's also using AI under the hood, and it was found, basically Elon Musk is CEO of this company, and they are rapidly innovating this project. So this, I think this year or last year, they already inserted this chip into human brain. And before, they showed the videos of the monkey playing ping pong just using their brains. And even if monkey can learn how to control this chip, for humans, it will be even more easier. It's using AI under the hood. This chip has 48 electrodes, and each electrode has a lot of, like, more than 100 sensors. So this, in each sensor gets electrical information from brain neurons. And after that, these signals getting translated into actions in the computer. And this translation is happening using neural network. So this is basically decoder, where we have to decode electrical signals from human brain into computer actions. And how to learn how to do this? It's basically very easy. When human gets this chip, he will start to see how the cursor in the computer reacts to his thoughts. He will basically start to navigate it. He will first realize how it's reacting to his thoughts, and it will quickly learn how to manipulate computer. And after they improve this chip by including more electrodes and sensor, we can encode much more comprehensive signals. Like we can basically talk without real communication, like telepathy. We can send our messages just by brain, and we can program using our brain, and even probably much more advanced stuff we can do, which we really don't know yet.
So basically, if you put this on, so there's nothing you're gonna be able to hide anymore with this on. Because even if you physically don't make the action happen, it still understands what your intent is, or what your thought was, even if you didn't perform the action.
This is partially true because the problem that each brain is unique and it has its own unique intentions encoded, and they're encoded differently. For example, in your memory, you have memories of your car, and that will be located in a specific area of the brain. For another person, it will be a completely different location. And there are some common patterns that can be probably studied later on, but it will not be very easy to create general model that can read any human minds. I think you have to create each person's specific model that can read only your mind. But this is possible. I think they can actually create encoders that can visualize all your thoughts.
Yeah, I believe possibly for every individual, as you said, part of the individual's metrics are different for the output of his actions. So you can't really generalize, have a biases on what the input would be for a certain result. But if the model is constantly on a flywheel training itself for that specific individual, it only gets better at understanding that personality or that source of information, and eventually it'll train itself to inference everything that's needed.
Are you afraid that it will start to control you?
Maybe if there's some sort of reverse engineering in the neural system of the brain, maybe. But what I'm saying is like at a lower level, like being able just to understand everything that you're doing, like whether it's like an emotion, you want no more privacy, right? So it'll know that it's there, even though you're not sure.
Yes, it's true. One more question?
Yeah, I guess as a follow-up on that, are you saying that in the future there might be like a general AI that can read all of these thoughts, or are you saying that with the current models they can achieve that? My understanding is that these are very narrow. Like they can't see as a monkey can sell out a banana. They can only, yeah.
This is a very simple model that is just an interface to make very simple actions in like click the mouse or move the mouse or some very basic and easy stuff. But moving forward, they will create very advanced sensors that can get signals from hundreds of thousands or even from millions or billions of neuron cells. Then it will be able to decode really comprehensive and advanced thoughts, like your memories from the past, your imagination, your thoughts, your intention, behavior, your feelings, and so on.
Thanks. And I have a question myself. So I was watching the Elon Musk and Lex Fridman podcast, and they were talking about bits per second, right? And the transfer speed between brain interface. And I was wondering what your thoughts were. Because Lex was asking him a question. What do you think is going to happen when we get to very high numbers of bits per second? Where do you see? What do you see as our potential? Will we be able to? I mean, how much more advanced will humans be at that point?
I think it's a very good question. I think it's like we can use all our creativity to think about it. If you have a very huge amount of information being processed, it can go into both directions. It can stimulate your brain, or it can read your brain. And in terms of reading your brain, like I said, it can basically understand everything about you. But in terms of stimulation, probably there are pros and cons. It can probably treat depression or other mental diseases. However, it can actually create intentions in your head. I'm sure at some point they will learn how to do this. At some point they will learn how to cause feelings like aggression or love or empathy, or they will learn how to disable them or enable them. This is scary, but this is our reality. We have to be ready for that. We have to take advantage from it.
Thank you for the knowledge.
Another field that...
One more.
One more question?
Wow, wait.
Yeah, sorry. Go ahead.
Yeah, exactly.
Okay. Another field that rapidly being transformed is robotics. And the reason for that with recent breakthrough of large language models, we actually created human-to-computer interface. And this is a very natural interface where we can translate human language into computer commands, like to adapt to any API. And robots is like a computer which has a lot of functions, and currently each of the functions can be accessed using API, basically using program. But with natural language, we can actually access this interface. We can create command, like by saying things, and a robot will do some work for you. You can tell, okay, bring me the water, and it never got trained to bring you the water, but because it has very generic understanding of the world that encoded into a large language model, it will understand what you want. It will understand your intention, and it will understand how to solve your task based on reasoning capabilities. And like next generations of foundation models will be multimodal. Like today, you probably saw a presentation from Google. They also introduced a Gemini multimodal that can get visual signal, speech signal, and text signal. And all these signals together create a world model that can be used by robots. And they can transform any commands into the actions very easily. So you don't need to program like very specific tasks. You have foundation model that can be used by these robots. The only challenges we have currently is engineering challenges, but they will be solved very quickly. Like in several years, we will see a lot of androids working in the different tasks. And one of the startups that got my attention is called Clone. It was founded in Poland, and they basically used the idea. So the evolution created very perfect systems for human labor. And these perfect systems, for example, a human hand has 26 degrees of freedom. It can solve very a lot of different tasks. But in existing robots has a much less degree of freedom, so it cannot solve really complex tasks. It cannot catch the ball, it cannot make sophisticated movements. But if we replicate all the structure of human body, like we print bones, we print every muscles, make it functional, and we put brain there, and brain already exists. We have world model, multimodal neural networks. So this thing can actually work. And another model is was created by DeepMind. They trained robots to play ping pong on the human level. So it's not a very professional player yet, but it's middle level already. And I'm sure next year they will create model that will perform on top players in the world, and it can be used as a trainer. And this is just one task. And machine learning can solve any task in the most effective way which is possible. And in terms of sport, I'm pretty sure that these robots will become really, really good. So I think I finished the first part about frontier AI. Maybe we can have more questions, and before we switch to PyTorch Lightning.
Question here?
I kind of came in 30 minutes late. You know, this Miami traffic bridge went up and all that stuff. So I'm just trying to get an understanding of. So when I came in, you was talking about Alpha Zero. Now I want to make sure I'm understanding it. Once again, I kind of came in after you had already been well into the presentation. So Alpha Point, is that a form of neural network that's being used to do what exactly?
Yeah, thank you. Alpha Zero, it's the machine learning model, the approach that was invented by DeepMind. They use state-of-the-art reinforcement learning model to improve any systems. For example, first of the applications that they made was a game called Go, and it's like chess but more advanced, where you have infinite amount of combinations. So it's impossible to program all of them. And they created a reinforced learning algorithm that plays with themselves for thousands and millions of games. On the cluster of thousands of GPUs, it plays a lot of games, and it learns how to win. It learns hidden strategies, how to win any games. And at some point, they beat world champion in the Go. Then, next generation, they use this approach, reinforcement learning approach, to solve fundamental problems in the natural science, like in physics, in biology, in chemistry, in math. They use this model to solve humanity problems. And we were talking about these problems like nuclear fusion, another powerful source of energy, clean energy. We were talking about protein folding. It's a problem from biology that is used for drug discovery, and it was also solved using this Alpha Zero. There's a model for math Olympiads. So this model can actually solve math problems, and it was used for for materials discovery. So this tool is extremely powerful to solve real-world applications.
So Alpha Zero is the actual name of the neural network, or is that an app that's being used? Or is that the name of the actual neural network?
No, it's the name of the framework. Framework is like approach. So now we're going to talk about PyTorch Lightning. So this part will be very short. I'm not going to dive into details. I just want you to get familiar with the framework. So basically, the idea of PyTorch Lightning is like it's a next level of abstraction. So moving forward, when we create training script, neural network training script in the pure PyTorch, the code looks monolithic, and we need to handle everything. Like you need to make sure that backpropagation step was triggered. You need to make sure that metrics were updated, loss was calculated at every stage. And especially it's getting harder if you need to scale it. For example, if you have to create state-of-the-art training script that use early stopping and other advanced tricks, and especially if you want to train in a multi-GPU cluster, it's getting very large and it's very hard to support, and it's very hard to replicate. Lightning is a modular framework where you can create wrappers on top of this, on top of your model. Basically, you transform your training script into the object, and you have to define state of the object and its behavior. So, and another good thing about PyTorch Lightning is that device management is handled automatically. You just need to set a list of devices, and it will automatically shard the data across devices. You don't need to specifically define which chunk of the data will go to which specific GPU. It will be handled automatically. Also, you don't need to specify which devices data should go. Scaling also very easy to implement in the trainer. It's also well integrated with logging tools like this TensorFlow. It's very easy to log and control the training process. The only tricky part is debugging with PyTorch Lightning. So you can see PyTorch Lightning is like scikit-learn for neural networks. In scikit-learn, if you're familiar with machine learning, you just need to create object of the model, and you need to create your data set. You call function called fit and predict. It's just like 3 lines of code, and your machine learning algorithm works. And PyTorch Lightning is like the same similar idea. You define trainer in the its specific object, and you create your machine learning model separately, and your main code will be very simple. We can go and check their website. So one more good thing about PyTorch Lightning, they recently introduced a tool called Studios. Studios is like similar to Google Colab notebooks, where we have store for notebooks. So we can go and check like what are new models here. We can see how to fine-tune Llama. We can see how to train diffusion model. We can see how to deploy model. These are courses you can open and you can replicate very easy a lot of different projects here. You can go and see some results. It's very, very useful. Another thing, you can create a development environment inside. It will be similar to Vertex AI, for example, in the Google. You can integrate it with VS Code, and you can attach many GPUs, even 1,000 GPUs you can attach, and you can distribute your computation across all the GPUs. So, and this is how regular projects will look like. For example, your training script will be very simple. So we can, I'm sure if I can increase. Can you see what's written here?
So, 3-minute hold, please.
Better? So, like in scikit-learn, we create a model, we create a data model, we create trainer. This is core part of the PyTorch Lightning trainer, and we just call fit. You don't need to write advanced logic for your training, especially if you want to utilize state-of-the-art tricks for training. You just call fit and it will handle everything. And even for scaling, you can choose like accelerator GPU or CPU. You can set the devices, and if you have 8 devices, So the training will be handled on all of them, and you define strategy like just a configuration. And so you have to define, first you have to define your model, like neural network. Here you just focus on its architecture. You need to focus what layers you want to use, what activations functions you want to use, shapes of the tensors. You have to define its structure and its behavior in the forward function. And after that, you have to define the trainer object. It's like a wrapper on top of your neural network. And you have to define two parts here, state and behavior. In the state for trainer, we just create model that we recently defined. We create a loss function, we create a matrix, we create optimizer, and maybe something else. And then in the training step, or in validation step, in test step, we define its behavior, just how data being processed. So basically, just in the regular case, we just feed this chunk of the data into the model, get outputs, calculate loss, calculate metrics, and log it in TensorBoard. This will be automatically captured in TensorBoard. Same similar we do for validation for test. We don't need. So I think here we can configure optimizers. And one more thing is in PyTorch Lightning, we can set callbacks. So, and in these callbacks, we can use, for example, early stopping callback, or some other, what else, I don't remember. So, like many callbacks you can define here. For example, how we work, we have YAML file. It's like JSON configuration, where we just define set of callbacks we want to use, its parameters, and some additional information. And then we have a fabric that creates all callbacks based on YAML config. And we set all of them, we feed all of them into the trainer. And everything really advanced training script will be training under the hood. We don't need to control this logic. So I think this is it. I think we are good here.
Quick question.
Yeah.
Is this framework open source, or you have to do the training on their platform or infrastructure?
It's open source. You can install it and.
Okay, and then I can use any other provider to do the training for me. I don't have to use them as a.
Yeah, it's just a library. You just use library. You define the wrappers, and that's it. It's like additional layer of abstraction. So you're going from machine learning architecture, model architecture. You have next level of abstraction on the training level. You have to define the logic of how loss function being calculated, how metrics being calculated, and maybe you have multiple models that, for example, in GAN, we have multiple models, and we have some sophisticated loss function. Here it's very easy to handle. And it's very easy to support. When you have modular code, you have to update one part, and it can be reused by other components. If your code is modular, it's easy to support.
Two questions. Does Lightning give you any performance benefits over vanilla Torch? And or is it just meant for abstraction, just so for code organization, you don't really get anything more than that?
Yeah, it's just abstraction for code organization. For example, for lazy engineers like me, it's a great tool because I don't want to every time to dive deep into the training loop, understand, okay, what's not working there, because you never. It's very rare that you have to change it. You just need to update. We created very advanced logic using this. For example, we select some specific chunks of the data to calculate different loss functions, and it's very easy to handle here. So in terms of performance benefits, no, you will not get them.
Also, how does PyTorch Lightning handle multi-node GPU training as well? Does it abstract just on top of existing? Like,
yes, it abstracts on
PyTorch?
top of existing. Yes, it uses existing Torch libraries, but it just less manual work. You don't need to define this samplers. You don't need to define sharding. You don't need to define like the logic how to process chunks of the data between devices.
But you
So
still have to
it's
pass
handled
in,
automatically.
you still have to pass in configs about
Yeah.
what your topology is.
Yes, you define the GPUs you want to use. You define the strategy. There are different strategies for distributed training, depending on you have just multiple GPUs, or maybe you have different number of machines. This number of GPUs, there will be different strategy for distributed training. But basically, you just set the configuration, and everything else is handled automatically. For example, I never did distributed training before, but with PyTorch Lightning, it's so easy. Then I checked in pure PyTorch, it's like more headache. You just need to learn more new things, how to organize it. It's like, yeah, you just can take and use it.
I guess the last question. How does your infrastructure have to look when you're doing multi-node training in Lightning? Do I have to run like multiple of these training processes in order to allow them to sync?
Oh, this is a good question. So when you start distributed training, it will initiate multiple processes. So for each GPU, you will have separate process, and you can control them. There is a rank, global rank. For each process, you can get its rank, and you can recognize which process currently is executing. And so since you have multiple processes being run, you can actually use multiple threads to distribute the data. For example, in data loader, you can also use multiple threads, which will accelerate your pre-processing stage. And you can also use there's a built-in profiler. You can see how memory is being utilized, how much time each call takes. So you can go very deep in terms of profiling of the performance. But under the hood, it's using the existing Torch libraries, so it's nothing really special. It's no CUDA drivers, it's just existing Torch libraries.
I got two more questions. So, this was a library made by Meta also,
No.
but and is there going to be any need for the older Torch, or can we just rely on this?
I'm not sure who created this library, but it's not Meta. I think it's just a community.
Can we rely just on this and not worry so much about the older PyTorch anymore?
No. This is just a wrapper on top of PyTorch. So it uses wrapper, which saves your time. You work less. You need to control less code base, because a lot of the code base will be hidden under the PyTorch Lightning infrastructure.
If you needed to tweak that, would you be able to on PyTorch Lightning? If you need to go in and tweak that code base that is already modular?
Yes, it's open source. Yeah, you can change it.
Amazing. Any more questions?
I'm curious. You were saying that you can distribute across different GPUs. Would they all have to be like NVIDIA, or could I use multiple different brands?
Oh, this is a good question. Let me think. I think since it handles multi-machine strategy, I think it's possible. No, I'm not sure. I'm not ready to answer this question. So in our system, we use just NVIDIA GPUs. We don't have like mixed data centers.
Any last questions?
The one like incrementally adopting Lightning. It sounds like you can just take whatever existing Torch model you have and just wrap it Lightning module, and it's that easy.
It's just a wrapper. You just create wrapper instead of existing training script. You create a PyTorch Lightning trainer, and you copy the parts of your training loop inside training step. And for validation, the same for test. And in the state of trainer, you create your models. You define your models and loss functions. So, for example, you can introduce code refactoring. Like if you feel that it's hard to support existing training scripts, you have like a lot of models, a lot of experiments, a lot of different training scripts. And if you want to organize it, you can just use existing scripts and transform it into Torch Lightning.
So if I want to have my production training run, I can leverage Lightning for that. But for say local experiments, I want to mess with the loop a little bit or try different things.
Yeah, even if you have problems with environment in your runtime, you can extract the pure Torch model from PyTorch Lightning model. It's just a trainer, and you can get your Torch model and work with a pure Torch model. For example, we had some restrictions in runtime, and we didn't use Lightning libraries in the production inference environment. We just use a pure Torch model.
Have you written callbacks as well for the trainer yourself? Are they easy to implement?
We use the existing callbacks. I haven't implemented my own callbacks. We use the existing callbacks. Like I remember early stopping and checkpoints. A few more. We just we created a YAML config file where we define which callbacks we want to use. We have Fabric that, depending on config, will create you a list of callbacks, and this list of callbacks will be passed into trainer. And I think it's the same way. If you implemented your own callbacks, it's absolutely the same approach. There's no different PyTorch Lightning or not. You just implement same callback, and it will be reused by the trainer.
So I'm curious about in your experience or other engineers or researchers that you know, the split in industry between doing more researchy things versus doing more engineering types things. And especially when you're trying to make a model to predict something like churn, there's probably some research phase that happened, and maybe that's less so now. But I'm curious what the split is, or what the split for you is,
I think most of the time we work on the data. Research and modeling is like a very small part of the work, and engineering is also not a big deal. Data, I think it's most of the time we work on the data. And this problem is like tabular data prediction. It's like very well studied. We use deep learning not because it has better accuracy. It's because so we can do like multitask prediction. Like we can incorporate like many tasks. We can create many heads for a neural network. And actually, if we have an extremely huge amount of data, like we do, neural networks actually outperform tree-based models even for tabular data. Neural networks are very great for unstructured data like image, text, video, sound, but for tabular data, tree-based models are state-of-the-art. But if you have really huge amount of data, you can create effective architecture of neural network that will outperform chip-based models. Thank you for the very great questions. Great discussion.
I think I speak for all of us when I say that that was an incredible presentation. Thank you so much. We learned so much from nuclear fusion through protein folding all the way to PyTorch Lightning, a really great wrapper over PyTorch, and really provides a lot of great abstraction and makes it so that it's easier for us to develop an AI. So thank you again, Aleksei, for that amazing presentation. And this is what we do every week here at GP Tuesday. We provide amazing education. We bring the AI community together so that we can all learn from one another, so that we can stay ahead of the AI wave of change. Everything's moving so fast, so by learning together and working together, we'll be able to stay ahead and be able to also share with the world about what we learned here. There's actually a lot of great conversations that are going to happen, I think, within this room over the next years, weeks, months, years, that might actually shape the future of the world, right? Because this is what we're talking about now. Things are moving quickly, and it's really exciting. So thank you, everyone, for making it today. I'm looking forward to talking with all of you and getting to know you. So just some last pieces of information. There's please, everyone, if you enjoyed your time here today, please go ahead and share on social media about what you saw here. Tag GP Tuesdays and go ahead and share that. Pictures, anything on LinkedIn, Twitter, Instagram, all that fun stuff. We're also, so go ahead, please. Go ahead and share everything you see. Also, the parking validation in the front, so please go ahead and grab that. If you park in the parking structure, that'll give you a nice discount for only $10. So there we go. And beyond that, I think that's pretty much it. Oh yes, thank you so much. Telegram group. Can't forget that. We have a great Telegram group of over 250 people now. So that way you can all stay connected with each other every single day. We share a lot of news in there, conversations in there, and generally we just all have a great time in there. So great. Please share some memes and gifs. Can't go wrong. And there's food and drinks in the back, so please make yourself comfortable and happy and full. Beyond that, let's just have some great conversations. Thank you.
Yeah, what is the Telegram group?
Yeah, the Telegram group is, I'll go ahead and put it on the screen here. And yeah, I'll go ahead and put it on the screen here so anyone can follow in. Thank you.
Just had a friend over, made it to the States, and hosting.
Cool.
Thank
you so much.
How are you?
From the Metro Cafe.
Oh yeah. Georgie came.
Yeah. How you guys, man? Good, yeah. Amazing time. You follow on live stream. I'll share the YouTube with you. Oh, yeah. It's right there.
Right there? Okay, awesome.
Let me turn it off real quick.
Oh, yeah, for existing. It's never done before. You don't.
The idea that sample that a bunch of
Something. Let me know.